Hello, everyone. Thanks for coming back to the temporal graph reading group. This week, we are very excited to have Ivan here, who will be presenting their recent work at NeurIPS 2023, Taming Local Effects in Graph-Based Spatial Temporal Forecasting. And for a bit of background on Ivan, Ivan Marisca is a PhD student at the Swiss AI Lab, IDSIA and USI, Università della Svizzera
Italian
Italiana
Switzerland.
in Switzerland, under the supervision of Prof. Cesar Alipi. He received his master's degree in computer science and engineering from Politecnico di Milano, and Ivan's research focused on graph-based learning from irregular spatial temporal data with applications in prediction, imputation, and control on sensor networks. His work has been published in top-tier conferences in the field, such as NeurIPS, iClear, and AAAI. And in addition to his research, Ivan regularly works as a teaching assistant and hosts lectures in machine learning courses for master students at USI. He is also a co-creator and maintainer of Torch Spatial Temporal. And I will hand the mic to you, Ivan.
Thank you, Andy. Okay, I can share the screen.
Can you share the screen? Yeah, okay.
Okay,
Great.
Do you see it?
Yes, we can see you.
Okay, perfect. So thank you, Andy, for the introduction. So today I'll talk about this paper we published on NeurIPS this year about taming local effects in graph-based spatiotemporal forecasting. This is a joint work in collaboration with Andrea Cini that together with me led the research as the first author, and then also we have Daniele Zambon, which is here today, and Professor Alippi. So let's start. I'll start by giving an overview of the problem and the contribution of our paper. So we focus on the problem of forecasting in collections of time series. So when we have multiple time series where graph-based methods prove to be effective. And this is because the graph processing, so using graphs to process this time series, allows us to exploit the relationships that there exist across the time series. So in deep learning, this means that we combine sequence processing operators such as RNNs or TCNs with message passing, so with graph neural networks. In general, so combining these operators, we end up with a model which usually is actually a single and global, we say global inductive model. So we learn a function that can then be applied also to new time series, to new nodes, to new graphs in theory. But then what happens is that we instead usually inject some node specific parameters in the model, some local parameters that helps in identifying better the nodes and then tailoring the prediction for the specific node. And this allows us to model better what we call the local effects, so the dynamics which are specific for a single node, and this also yields to improved accuracy empirically. However, we lose the inductive capabilities that we have, because now when we have a new node or a new graph and we want to apply the same function, we no longer know how to treat this, how to use these local parameters, so these node-specific parameters. So in this paper, what we try to do is to understand the interplay between the globality and locality in graph-based models, and to propose a framework, a sound framework, to design these node-specific components in an effective way, and in a way also such as to ease the transferability of global, or in this case, global local models to new nodes, to new graphs. So we're trying to maintain again, or to restore the inductive capabilities of global models. I will start by giving an introduction on the problem and talking about the forecasting, a task under the lens of forecasting time series forecasting literature. Then I will move about on the spatiotemporal graph neural network part, so the part that we are the most interested in this talk, and talk about also globality and locality in spatiotemporal graph neural networks. And finally, we'll provide some empirical results on this topic. So let's start by introducing the problem. So we have a set of n correlated time series where each time series is associated at each time step with an observation vector. So we are assuming that each time series is multivariate, and at a given time step and node or time series, we have a vector. And paired with this vector, we have another vector of exogenous variables, which are any information that is interesting for the prediction that can help the forecast, but is not the target variable. To give a brief also the notation, we use the capital letters here to denote the stack of these observations across the time series. So we have capital X denoting all the observations in the collection. And we use this two notation here, so the colon notation to denote an interval, so a sequence from a time step 2 up to the second one excluded for denoting a sequence of observation, and the less than t symbol to denote the all the sequence from the beginning up to t minus 1. Now, besides the time series, we also assume that there exist functional dependencies among the time series. We can think about these dependencies as in a Granger causality way, so that using one time series to forecast another time series, if this yields improvement in the forecast, in the accuracy of the forecast, then we say that there is a functional dependency among these two time series, between these two time series. We can, of course, model these dependencies as a graph that in this case can also be asymmetric, since the dependencies may not be may have a direction. So we may have that a sensor, a time series influence another, but not the other way around. And we also call spatial this dimension, so the dimension that spans across the time series. Just to give an example, here we consider a sensor network that monitors the traffic speed. In this case, we are in San Francisco. We assume that there are, in this case, we have 5 nodes at crossroads, and so each node collects traffic measurement, and we have this the solid line here, which corresponds to the traffic measurement. Then we have also exogenous variables, the covariates for each node that may be the time of the day or the day of the week, some encoding of that. And we also have the graph, which is built using the rod network, so the underlying connections. Okay, on this setting, the problem of forecasting is the task of predicting the next H observations starting from a window of past VW observation, where VW is the length of the sequence. Now, in deep learning, this task is usually addressed by estimating this function f through a neural network. And we, in particular, distinguish two cases: the global case, in which we have a single neural network, which is trained to predict all of these time series. So we have the same network with the same weights, which is applied to all the time series. Or we may have a local approach, in which we have different different models with different weights, each applied to the time series independently. Now, a global model is called global if the parameters are fitted to the group of time series together. So we have a single model and it's applied to all of these time series. The local models instead are specific to each time series. This means that a global model shares the parameters across all the time series. So we have more data available to train the same amount of parameters, the same parameters. And also this means that we can use the model in an inductive learning setting. So if a new time series arrives that comes from the same or similar data generating process, we can use the same model to produce the forecast. Instead, in the local case, this is not true. We cannot use a local model to a new time series, or it's difficult how to it's not trivial to understand how to apply a model to an unseen node. However, we are better in capturing the dynamics which are specific of the time series in using a global model. Now, there are results in theory that say that an enough capable global model with an enough input window can, in principle, learn the same dynamics that a local model can do. But empirically speaking, a local model needs shorter input windows and a reduced model capacities to learn the same in the same way the patterns, the local effects, so the dynamics which are specific of a single node. Both of the approaches, however, are discarding the dependencies that there may exist across the time series, because in both cases we are treating all the time series independently. So the idea here is to embed this relational information that we have, so the graph of the dependencies that we have, as an architectural bias. So to use, in this case, graph neural networks to process the spatial dimension, so the dependencies across the time series. The models that of this kind are called spatiotemporal graph neural networks in literature, and have the advantage of being global models. And so we have we are sharing the parameters. We still have the inductive capabilities, because here we are learning a function which is shared across all the nodes. However, differently from before, we are conditioning use through message passing all the forecasts on the observations at the related time series. So when we are forecasting the blue time series, we are taking into account also values from the green and the yellow. Then if we propagate also for more than one step on the graph, we account for all the time series in this case. Now, on this work, we consider spatiotemporal graph neural networks that can be expressed as a sequence of 3 operations. The first one being an encoding phase, in which we encode all the information that we have at a single node and time step in an initial representation, H. This is typically done by a linear layer or an MLP. Then we have a stack of L spatiotemporal message passing layers, in which we refine this initial representation by relying on spatial and temporal dependencies. So by exchanging information along time and space. And in the end, we use the final obtained representation at each node to produce the forecast by means of another MLP, usually, so a decoder layer. The cornerstone operator is the spatiotemporal message passing, which is very, very similar to the standard message passing by Gilmer et al., in which we have a message function that here instead the main difference is that we are working on sequences, right? So the message itself takes sequences as input and produce another sequence or a vector, and then we aggregate all these messages from our neighbors, and we update the feature by using also the previous observations of the root node. Now, here we have the same issues that we had before for global models, so they may struggle to model local effects, or might require large model capacity or long windows. And both of them may be an issue in this case, because scalability is a concern when talking about spatiotemporal data. So the idea is to use hybrid global local STGNNs that have specialized local components. So in this case, we have a part which is global, and we have some components which is local instead. And these components are the one in charge to better capture the node level effects that we have. And also, as I said also before, doing this allows usually to obtain empirical, a higher empirical accuracy. However, again, when we introduce these local components, we break the capabilities of the model of work in inductive setting. So it's now hard to handle the unseen time series, and also the number of learnable parameters can be larger if we consider that we are specializing each of these components for the time series at hand. So one idea is to mitigate all these drawbacks by means of node embeddings. So node embeddings are a table of learnable parameters where for each node we have a vector, just a vector of parameters. And then we can use these vectors, these parameters in some components of the STGNN and learn them end to end within the architecture. So just to give an example, considering our STGNN, we can keep the model global and then just condition the encoding or decoding phase by including in our function these parameters. So basically, the main part, so let's say the weights that we use, the parameters that we use inside this function are shared across all the nodes, but we have this single vector which is responsible for tailoring the prediction for the specific time series. And now the important thing is that we can reuse the same vector also for different parts of the network. So in this way, what we the advantage of using node embeddings to specialize an STGNN is that we are amortizing the costs of specializing the model to each time series, because now we have a single vector that are maintaining for each of the time series. And also this allows us to ease the transfer to another graph, to another or to new nodes. Because now what we have to learn when we have a new set of nodes or just a new time series is just a vector, because we can reuse all the parameters of the global part of the model which is shared across all the time series. And also, if we regularize this embedding space, we can also find a way to accommodate for new nodes or new embeddings in a better way. Now, on this part, we we propose two regularizations. The first one is a variational regularization, in which the goal is to obtain a smoother embedding space in which interpolation is possible. So we assume that this embedding comes from a multivariate Gaussian distribution, and so very similar to what is done in variational inference. With we learn a distribution over the embeddings, and in this case we can during training we explore a deeper area of our embedding space, and then we are able to accommodate for more embeddings in the same space when new embeddings arrive. The second regularization is a clustering-based regularization, in which we incentivize clusters in the latent space. So this also yields to an improved interpretability. To do this, we basically add a matrix of learnable centroids instead of the embeddings, in which we have, instead of having n of these embeddings, we have k of them, with k which is very smaller compared to n. And then we learn another cluster assignment matrix, which instead which gives scores of the node cluster pairs. And so we then basically use the Gumbel softmax trick to assign each node to a centroid, a cluster, and use the embedding of the cluster. So in this case, we we will see then an experiment on this in which we can then distinguish the different clusters in the embedding space. Now, some empirical results. These are on real-world benchmarks. So we have two traffic forecasting benchmark, a dataset on energy, on load consumption, so energy consumption and air quality. We consider both state-of-the-art SDGNNs from the literature, as well as some reference architecture which tries to implement a streamline architecture just to see the effect of using this embedding. We also consider an RNN, which does not contain any module that does graph propagation. So we have just we are treating the different time series independently, as we saw in the beginning. And we compare the global model, or the original in case of the state-of-the-art architecture, with respect to adding the embeddings at the encoding and decoding stage, as we saw before. So here we can see that the bold number, a number is in bold if it's better compared to between the global or the variant with embedding. And we can see that in most of the case, we have an improvement when we use the embeddings, which is in the case of the reference architecture is very high. And in some cases, we can see that also simple models like the RNN that neglect the spatial dependencies can reach performance which are very close to spatiotemporal models with respect to the global variant instead. And interestingly, we also can see that models that are a bit outdated so far, with the DCRNN was one of the first one proposed in 2018, and by introducing the embeddings, we can reach performances which is very close to other network which are more complex. In this last experiment, instead, we show the effect of regularizing the embedding space. In this case, we trained a single model, graph-based model, on 3 datasets for traffic forecasting, and then we transfer the learning on a new dataset and evaluate the performance on a new dataset, which was unseen during training. So the idea is that we consider both a global model or a model with embeddings, and see if if regularizing the embedding space while learning, while training in the first on the first 3 datasets, then yields improvements when tested to a new dataset. So here the global and zero shot are the global models, which are taking in this case here, the zero shot, we just freeze the weights after the training and test on the new dataset. Here instead, we are retraining the model on the fine-tuning set that we have, and this is the number of data which is available in the fine-tuning set. So as we while we go to the right part, we are decreasing the number of samples available in the fine-tuning set. And we can see that in these cases, the regularizations help in improving the accuracy. And this is also more evident when we have few number of samples available for fine-tuning. As for the interpretability part, instead, here we plot the time series associated with the clusters that we learned in the embedding space. And we can see that here we had 5 clusters, and we can see that among each cluster, within each cluster, we have some clear pattern of the time series associated. So we have, in this case, we may have different, these are enterprises. So the consumption in a week of different enterprises. We can have bars, pubs, we can have also offices. And so we see that there is a difference on the some seasonality, which is daily, and also a different maximum or peak our also maximum capacity for the different clusters that may be due to the different type of work done in each of the nodes, so in each of the enterprise in this case. Okay, so the code for all the experiment is available online in our repository that is here. I also give a pointer for our open source library on spatiotemporal data, which is torch spatiotemporal, which is built upon PyTorch and PyTorch geometric to accelerate the research on neural spatiotemporal data processing that can be forecasting, imputation, or other tasks, and where the focus is on graph neural networks. Sorry. Okay, yeah. So thank you all. These are the people that work in this research. In this website, you can find all the publications that we had. And yeah, thank you for the attention.
Great. Thanks for the very nice talk, Ivan, and it was very clear. And for the audience, feel free to type any question in the chat or like interrupt us, like if you want to ask the question yourself. I just want to have a clarification question first. So
Yes.
how do you transfer to the new data sets, like exactly from
Perfect.
the embeddings?
Yeah. Okay. So basically here, okay, here we have all the gray box here are the global part, let's say. So the gray part here can work out of the box for new nodes, new graphs. What we do when we do the transfer part, we freeze this gray part here, so all the weights related to this part, and what we instead have to tune to train actually are just the embeddings. So what we do is just to discard all the old embeddings that we had for the nodes in the training set, and we assign new embeddings to the new nodes. We freeze these gray components, and we train for a fixed number of epochs just the embeddings. So you can think about it as if you have this function which is learned, then you have this random vector and for each node, and then you for each node you're trying to position it in the space in a way that then you can maximize the forecast for that specific node.
Right. So you kind of learned the node embeddings a little bit on the new data that you are provided.
Exactly.
And then the rest is basically frozen. Okay.
Exactly. Yes.
That makes sense. There's a question from the chat.
Yeah.
From Anik. What is the impact of graph structure information on the performance of the model?
Okay. Okay. So coming back to this part here, when we do not consider the embeddings, we can see here this RNN is the only model that doesn't have spatial information, so doesn't exploit the dependencies given by the graph. And here we can see that there is an advantage of using graph-based model with respect to a temporal one, a purely temporal model. When we add this embedding, the things changes because we now are able to lower the error made by the temporal based model, and in some cases, as in this Pence Bay here, we get really close to the best result. So in this case, what we can say is that we need to localize somehow the prediction. So a purely global model with this fixed capacity and window that in this example was 1 hour of observation and to predict the next hour the traffic datasets, and a global model which is purely temporal fail in obtaining good performances. When having a graph instead, we are somehow localizing this information by also conditioning on our neighborhood. The embeddings in this case can help us in giving a better a better identifier for the single for the specific time series. In other cases, instead, like in the air quality dataset, instead, the performance gap remains when we consider the graph. So even when we have the embeddings, considering the information of the neighborhood can be beneficial. And in this case, it's particularly interesting because the air quality dataset has a lots of missing values, more than about 25%. So a possible interpretation is that using the graphs or conditioning on a neighborhood allows us to filter out somehow the noise introduced by missing data.
That makes sense.
Don't know if this answers your question.
Yeah, I think it does answer the question. Thanks for the nice answer. And also the metric that you report in this table is the mean squared error.
Yeah, the mean absolute error. Yeah,
The
it's
absolute
missing,
error.
sorry. Yeah.
Do you know, just out of curiosity, why the CERE data set is orders of magnitude larger error than the other ones?
Yeah, it's okay. In these cases here, yeah, the mean absolute error has always this problem of that you always have to compare to see it in a relative terms with the other values. In this case here, we are considering megawatt, if I am not wrong, of
Okay.
consumption, or kilowatt, sorry, kilowatt, and yeah, it's basically something which is related to the unit of measure that you are considering. Here you have
Okay.
values that ranges from 40 to 60 or more or less, and here you have something that instead can go up to 9,000, 5,000, something like that. So
Okay, that makes sense. Yeah, thanks for the thanks for the talk again. I do have
thank
one
you
more
all.
question, but it's not as
Yes.
related. It's more just a discussion. So,
Okay.
when you were talking about the global and local model, I was thinking that, like, for example, if you go back to the slides where you had the nice visual with the graph and the time series, yeah, I think this one
This.
works too. So
Okay.
basically, so I don't know how many nodes you usually have in the graph. Because they are time series, I suppose there's not like thousands of nodes, right? So it's
Mm-hmm.
uh like at most 100. But there's also specific graph motifs that you can see from the graph structure here, right? So maybe there are subgroup of time series that are highly correlated with each other, and this subgraph should be isolated to be learned together. So kind of like in between the global and the local. So local is for each node and global is for the entire graph. But then maybe some model potentially can work better if you just look at specific subgraph that are very densely connected. So assume they have very high correlation with each other, and the other time series don't affect them as much. But I don't know if that makes sense.
Yeah. No, it perfectly makes sense. Yeah, a possible idea indeed in this case is to have also these embeddings which are somehow hierarchical, for instance, right? So
Right.
you may have this is very related to the clustering part here, in which you don't learn an embedding for each node, but you learn an assignment to some centroid. So you can do something similar in which you say, in which you learn some hierarchy of embeddings, in which you try to maintain the embeddings for each node as close as possible in each layer of the hierarchy.
Mm.
Don't know if it makes sense.
Yeah, that makes sense. Yeah, so it's kind of you have a hierarchical relation in the graph on
Yeah,
which nodes are forming clusters. Yeah.
yeah, exactly. But then an important thing here is that the embeddings are not necessarily related to the graph. So you may have a graph structure that help you in learning the global dynamics that you have, but then you have an embedding that allows you to distinguish, in some cases, the node, the specific node from your neighborhood. So it's not always true that the embeddings of closed nodes must be close in the embedding space, but in some cases you may also want to have it really far apart, just to being able to distinguish that node from your neighbor. Maybe because that node has a specific local dynamics which are very different from the neighborhood. But still, you need to learn a global function in which you consider your neighborhood because the global dynamics are shared. Okay.
Yeah, that makes sense. Yeah, so it's not just depending on the graph structure, but also specific noise on the
Exactly.
individual nodes and so on and so
Exactly.
forth. Okay. Yeah.
Yeah,
Great.
exactly. The advantage, you're losing too much when if you think about the inductive capabilities of the model, because the the useful among the other, one of the useful property of the GNNs is the inductive capability. So you just have to you just need a node and a neighborhood, and then you can apply the same function. And so you can do it also on new nodes and whatever. And you are losing this important property to introduce something which is really specific, really tailored for that time series, and this then being as expressive as possible is what you can do to to at least mitigate the problem that you're introducing.
Yes, that makes sense. Okay, another question from Anik. What is the look ahead step? So how many steps do you predict for the forecast?
Okay, for the traffic dataset, we have 1 hour input, 1 hour output. It's 5 minutes sampling. The sampling rate is 5 minutes, so we have 12 and 12. For the air quality, we have 24 hours and we predict 3, if I'm not wrong. And for the and the same should be for the and load forecasting dataset. Yeah. Yeah, it's we have all the details in the paper. I may be wrong with this, the last one, but the other one I'm pretty sure.
Okay.
So it's
Great.
it's not, yeah, it's none of them. It's for long range forecasting.
Okay. Thanks. I think that answers the question as well. Sounds good. Thanks for the great discussion and the talk. So if there's no more question from the audience, then we can like wrap up the talk here. And we'll also share the talk recording like on YouTube for people to see. And yeah. Okay. Are there more questions? Okay. Okay, so we'll just wrap up the talk here. Thanks everyone, and see you next week.